Hey everyone, welcome back to The Explainer. I'm so glad you're here with us today. Just right off the bat, I want to give a quick shout out to Forge College for bringing us this explainer. Okay, so today we are literally putting on our hard hats. We're in the From EVM to SVM track, and we're tackling a massive but super fun task. We are taking Ethereum virtual machine blueprints and translating them into solid, reliable Solana structural engineering. It's kind of like a giant puzzle. And by the end of this, you're going to see exactly how to map those core concepts over smoothly. Let's get into it. Now, you might remember from our previous lesson, we spent a bunch of time setting up the perfect development environment, right? We organized the workspace, pinned our dependencies, set up our local test harnesses. Basically, we bought the tools and set up the workbench. Well, now it's time to actually pour the concrete. We're going to translate our actual smart contract logic and see how it holds up in its brand new environment. So here's our architectural manifest for today. We're going to cover the blueprint translation, then mapping state and storage, translating logic, explicit error handling, and finally inspecting the port. All right, let's dive right in. Starting off with Section 1, the blueprint translation, mapping old concepts to new paradigms. Look, EVM and Solana, they're fundamentally different structural paradigms. I mean, you literally can't just paste a brick wall onto a suspension bridge, right? It doesn't work. We have to really understand the new rules of physics here before we write a single line of code. And that brings us to absolutely crucial concept number 1, behavioral parity. This is our North Star for the entire project. Basically, it means that no matter how radically different the underlying code looks on Solana, our newly ported program has to produce the exact same observable outcomes as the original EVM contract. So if a specific input caused a certain change on Ethereum, it needs to cause that exact same equivalent change on Solana. Simple as that. It's our ultimate guiding principle. To help with that, think of this table as your essential translation dictionary. Over on the EVM side, a contract storage slot? Well, on Solana, that translates into a single account storing a serialized struct. What about an EVM mapping? On Solana, those are separate program-derived addresses, or PDAs. Instead of checking a global MSG sender, we're going to write an explicit is-signer check. And instead of a revert, you'll return an explicit err. Definitely keep this dictionary handy in your mind. Okay, moving on to Section 2, mapping state and storage. Let's actually transition to the construction phase, starting right at the foundation. Where does the data actually live? So think of EVM storage like a massive centralized state tree. It's kind of like one giant filing cabinet where every single piece of paper is just stuffed into various folders. Solana storage, on the other hand, is decentralized right at the structural level. It's more like moving to hundreds of individual, highly secure briefcases that are just floating on the network. Every single account is its own isolated container of state. So how do we actually build one of those briefcases? Well, we define a state account. And using anchor-style derives, we keep it incredibly simple and small. Step 1, we just define the struct itself. Step 2, we add an authority pub key. This is basically the equivalent of our EVM owner address, the person holding the keys to that specific briefcase. And then step 3, we just drop in a counter, just a simple unsigned 64-bit integer to hold our state data. It's simple, it's lightweight, and it is perfectly tailored for the Solana network. Now that our foundation is poured and our data briefcase is built, we've got to add the moving parts. That brings us to Section 3, translating logic, handlers, and state changes. Obviously, we need functions to actually interact with our state, right? So first, we implement the initializer handler. Now, in the EVM world, this would just be your constructor. But on Solana, it's an instruction that literally creates the state account, zeroes out the counter, and sets the admin authority to the provided signer. Then, we implement the increment function. This is our state mutator. It takes the context, reaches right into that specific account, and increments the counter in place. And this leads us to another core principle. Choose explicit account ownership to mirror EVM owner semantics. I really want to emphasize this because Solana doesn't have some magical global MSG.sender floating around that automatically owns the contract. No way. Solana requires us to be extremely deliberate. You absolutely must explicitly check the contexts and the signers to prove exactly who is allowed to change the state. But hey, what happens when someone tries to change the state and they aren't allowed? What happens when things inevitably go wrong? Well, that brings us to Section 4, explicit error handling, or as I like to call it, taming the reverts. I honestly love this comparison. In the EVM, an implicit revert is basically a toddler flipping a table. Something goes wrong, maybe an overflow, maybe an unauthorized caller, and the EVM just panics. It destroys the whole transaction, undoes everything, and just yells revert. Solana, though? Solana is much more civilized. Solana is like a polite bureaucrat handing you a neatly stamped denied form. It uses explicit result returns and custom error enums. The program just gracefully stops, hands you an exact error code, and logs exactly why it didn't proceed. To see this polite bureaucrat in action, let's look at a setAdmin function. Step 1, we add the handler. Step 2, instead of a simple require msg.sender equals owner, we actually manually verify that current admin.isSigner is true and that their key perfectly matches the authority on the state account. And if they don't match, step 3, we explicitly return an unauthorized error. We don't flip the table, we just politely hand back an unauthorized error. Oh, and speaking of taming errors, here's a quick but massive pro tip for you. Use checked add in Rust to preserve your overflow semantics. In EVM, arithmetic overflow automatically reverts. So, to get that exact same behavior, to maintain that behavioral parity we keep talking about, checked add will catch the overflow and let you convert it into a neat, explicit error. It perfectly preserves the original contract's guardrails. Okay, the logic is mapped, the errors are caught. Now it's time for the building inspector to check our work. Welcome to Section 5, Inspecting the Port, Validating Our Translation. We always validate our translation through rigorous local compilation and testing. So here's your checkpoint criteria. First, compile success, meaning 0 warnings, 0 errors. Second, unit test run. Your test harness should be glowing green. Third, behavior parity is achieved. This means the exact same inputs are yielding the exact same outputs and errors as the Ethereum version. And fourth, state invariants are preserved. The authority stored actually matches the admin used during initialization. If all of these check out, the structural integrity of your port is rock solid. But, what if a test fails? It happens. The golden rule here is to keep your changes minimal. If a test fails, double-check your account seeds and your PDAs to make sure they match the keys used in your tests. Check your serialization alignments. Just fix the specific assertion, rerun it, and commit incrementally. Small, focused code commits are absolutely your best friend when you're translating complex logic like this. So we have a working increment, it compiles, it tests cleanly and isolation, but that leaves us with a pretty provocative question, right? Does our working increment survive the chaos of the real world? Like, what happens when malicious accounts try to pass fake data, or when external programs interact in totally unexpected ways? Well, that is exactly what we are going to explore in our next lesson on testing and mocking. Trust me, you will not want to miss that one. Thank you so much for joining me today. Just a quick reminder, this explainer was proudly made by Forge College. If you want to master Web3 development and dive even deeper into translating EVM to SVM, or if you just want to explore a ton of other incredible Web3 topics, I highly encourage you to visit forge.college to learn more. Until next time, keep building, keep testing, and I'll see you in the next explainer.